Okay, well, welcome everybody. It's March 28th. This is actually the final of the 6 weeks of the these sessions. And I know Philip was just asking. Everything else will remain live for you up until, well, for a good long while. So access to the videos of this session, past sessions, are going to be open. The online course, I'll keep that open for at least a year. So if you want to continue to look at it, use it. Let's say you don't pass the exam the first go around, you have a free retake as part of the ETA process. So if you wanted to, you could go back and do a review and then retake the exam. So that's always an option. I'm confident every one of you will pass it on the first go round, but that's an option that's out there for you. I'm going to kick this into gallery view here. Everybody is hiding behind black screen, so I don't think it helps me much. But anyway, does anybody have any questions that came about while you were going through the sessions, going through any questions at all?
Oh, hi, Fahim here. And I was trying to go through the design quizzes on the online class. And there was this question about Greeley, Colorado, where you had to go to pvwatts.gov and figure out the insolation of that location. And I believe that has changed from what was in the quiz. So I think I had a bit higher number.
Okay.
And it assumed another number. And so the number that I put in was, I came up with wrong calculations, but that was it, really. Otherwise.
Okay. Did other people have exactly the same situation? I see Philip nodding. Okay, so yeah, that's good to know because the data does change, but I'm not aware of it changing. So I'll have to go back in and change that question. I just put Greeley, Colorado in there because that's where I was born. So we're going back to my old homestead. So I'll recheck the data.
Yeah, it was just a few decimal points here or there. So that was it, really.
All right. Yeah, that's one of those issues there was an interesting article talking about how, because of climate change, we're seeing an overestimation of how much some solar arrays are going to be producing, and an underestimation of what some solar arrays will be producing, depending on your part of the country. Most of these solar systems have traditionally been installed in the West, Colorado, Arizona, California, Nevada, those kind of areas. But with climate change, we're starting to see higher levels of cloud cover, increased heat, which tends to decrease the amount of output from the arrays. And since all of these systems are based on historical data, they're finding that there's an overestimation of how much power is going to be produced from the arrays by as much as 6 or 7%. So that's a big issue out west, especially if you're dealing with it as an investment, a very large installation where all of a sudden you're getting a 6 or 7% less return than you thought you would. Other parts of the country are getting better, like the Midwest, Ohio, Indiana, Illinois. We're seeing that the arrays will produce more than the historical data would tend to indicate. So, well, thanks. Fahim, I'll go ahead and go in and check that and make it, because I know it's always a little bit troubling. You think maybe you made a mistake when in reality you did it perfectly proper. Okay. Yeah. Any other questions? I've been getting some emails from students asking specifically about D-rate numbers in some of the design problems. The question might say, okay, the array is derated to 95% or derated to 90%, whatever. Unless the problem is specifically about how do you calculate a D-rate, usually those problems, I've just arbitrarily picked a number, just saying, okay, the system is 90% efficient. The system is 95% efficient. The numbers I've tried to pick are relatively normal kind of numbers you would find out there in the field. But the way you calculate your D rate is usually just from experience. So if you've installed a microinverter system and you've looked at how it's producing versus what it would produce if it were 100% efficient, and you find that you get about 93% or 92%, 94%, whatever, that you're going to use that number as your D rate. Actually, what I would suggest is you bump it a couple, under promise a little bit. So if you think it's going to produce 93%, maybe you say 90%. So your customer is pleasantly surprised as opposed to thinking that you did something wrong. So, but most of those numbers come from just experience. The big factors that go into the D rate are typically voltage drop, and you want to try and keep voltage drop to 2% or less throughout your system. The biggest one is usually the inverter's inefficiency, the cost of power in converting it from DC to AC. You can get that off of the inverter specs sheet. It's going to usually tell you it's 96% efficient or 93% efficient or whatever it happens to be. So if it's 93% efficient, then that means it's 7% inefficient. So that goes into your D rate. Another thing is if you're not using an optimizer or a microinverter, there's going to be panel mismatch D rating. So for example, if you're hooking up 20 panels together in a string for a string inverter, if the panel is going to operate plus or minus 5%, and that's not that atypical, some panels produce a little bit more, some panels produce a little bit less. But when they're all hooked together in a string, the whole string produces at the lowest common denominator. So if it's plus or minus 5, then it's minus 5. Everything's going to be producing at the lowest common denominator. That's one of the advantages of a micro module level power electronic is it does then get rid of that kind of pushing everything down to the lowest common denominator. So if it's plus or minus 5 and you've got microinverters, then it's 0, right? Because the plus cancel out the minus, everything's going to be on average what it should be. Same thing with optimizers. So that's how you create your D rate. Just throw things together. There's going to be losses due to connections, losses if you've got a charge controller. Another big loss is if you're using lead acid batteries. The internal losses when if you put 100 watts of power into a battery, you're only going to get 85 out. There's 15% internal losses in a lead acid battery system. In a lithium ion battery system, that you won't have those same levels of losses. You'll still have some, but it might only be 4 or 5%. Okay. If I don't hear any other questions, I'm going to jump into a design problem here. And let me see. I had trying to see the name here. Jason Hester, are you on the call here? All right. Well, we might design his system without him even seeing it. So
I mean, I am here, but I'm kind of listening and working. So
okay, well this will be recorded. So if I have a question, I'll shout it out to you.
Okay, I'm sorry I can't contribute.
Okay, that's fine. All right. Yep, he's changed his name to iPhone. So let me go ahead and go to screen share. So first thing you do with any design problem is you try and find the I don't see it here, is you're trying to find the electric bill. And the electric bill is, oh, there it is. Yeah, let me go back. I found it was in my email instead of. Can you guys see the electric bill here, or am I still on PV? Okay. Yeah. All right. This one should be. All right. So this is Jason's electric bill. So now you know everything you need to know about Jason. He no longer has any anonymity here.
I will say that I have a very large family that won't turn off lights.
Yes.
So that is part of my problem.
Yes. And if they're teenagers, just forget about it.
They all are. Yes.
Yeah, we raised our granddaughter, and when she was a teenager, we used to call her Miss America. And that was because she was 1/3 of the household and consumed 3/4 of all the resources. So that's why she was Miss America. All right. So your bill here, you're just showing us, and we can look month to month to month. So if I were to do a quick evaluation of this bill, I would assume that you've got air conditioning, which is why your summer months are a little bit higher. And I would also assume you have gas heating based on this. So I don't know if those are fair assumptions, but that's what I would.
That's accurate. Yes.
All right. And if we get down here, it's telling me that your average usage is 1,348 kilowatt hours per month.
Unfortunately, yes.
Yeah. Yep. And your bills look like they run around $200 a month or so.
Yep.
So, all right. So that's first step. So now we have your usage. So then the next step we would jump into is I would go to PV Watts. In this case, first I'm going to go to Google Earth, and let me see here. All right, so I pulled up your house here, and I'm going to keep looking at Philip because I can see you. Not if you can see his house here. All right, good. All right, so is this, I don't know if you can see, Jason, but it looks like this is your house. Okay.
Yes, that's accurate.
Yeah, and your roof pitch is difficult for solar. You've got an east-west. Got this little, what's this little white thing in the back? Is that like a patio cover or something?
Yeah, it's like a little gazebo that I built, and I was thinking that I could put solar on that as well.
Yeah, does that face south more or less?
It does. Yeah,
Okay.
It does.
Yeah, so that would be the ideal location as far as I'm concerned.
There is a section there. It's hard to describe, but it's right where your arrow is pointing. Go for right there.
Yeah, right in. Yeah, right in this area.
Yeah, correct.
Yeah, I mean, you could use that, but my guess is based on the size of your electric bill, that's not going to be enough.
Well, I'll say both.
Well, yeah, but I'd rather not split them if you can. I mean, you could, and you can run down, and that's all fine. But if I were really doing an evaluation deeply in here, I'd see if we could do it all in one go at one location on your gazebo. But it may be that you'll have to break it into two. And if you do have to break it into two, those would be the two sections that I would go with. The patio roof and then that section of your roof there. Where's your electric meter located? Is it on the side over on the east side?
No. Right there.
Oh, okay.
Yep.
Right on the south side. So so all of that gets full sunlight and all sorts of heat issues with it. But that's all right. We'll put a little cover over it. Actually, that's the best location for the installation, because you're going to just be running from this array over to there and down the side of the building to there, quite easily. So assuming you'd use a microinverter system, which is probably, in the market today for a residential home, you're either going to use a microinverter system or a solar edge system for the most part. With string inverters, the kind of calculations you've been doing, those are used in large commercial systems mostly, but and we can try and calculate it based on that. But my guess is I would recommend a microinverter system.
Okay.
And the way those hook in is you've got a combiner box that you would put right next to your meter, and then you would come in and you can hook up to 4 20-amp circuits into that combiner box. So it's very easy to run one circuit down from here on your roof, one circuit or 2 circuits over from the awning, and everything gets connected at that combiner box. So pretty straightforward. All right, so what we're doing here is we're just trying to get a sense of orientation. So what I'm going to assume is both of these are going to be 180 is true south and azimuth of 180. So I'm going to assume, let's say 170. I could figure that out exactly, but
that's about right.
So I'm going to put 170. And I'm also to measure the angle. And I know this is going to be 2 different angles because it looks like the part on the roof is at a steeper pitch than the angle of the patio roof. But we'll just assume a 20-degree pitch. That may or may not be right, but we'll do it for this calculation. It won't really matter. So at this stage, what we're trying to find is I'm going to say a 10% loss. So can you see now the PV watts calculator screen? Is that all right? So we're going to go with a 10% loss, a tilt of 20 degrees. And then I'm going to go ahead and change this to 170. I'm not worried about the size yet, because really all I'm trying to figure out is insulation. So we go in here, and now it's going to show me that at that pitch and at that angle at your location, it's going to be 4.44 hours of insulation per day.
Okay.
All right. So now, just as a review, how do we size? I'm going to bring up the whiteboard. So how do we size an array? Well, first thing we have to do is figure out the daily load, right? So from your electric bill, we know it's 1,348 kilowatt hours per month. So we divide this by, I like to use 30.5 days per month. And I'll need someone with a calculator to shout out a number. Anybody know what the daily load is then?
44.12.
44.12. That seems about right. Somebody else should probably check you, but we'll just say that's kilowatt hours per day.
I'm sorry, my rounding was a little off, Jay. It's 44.2. It's 44.196. So whatever.
All right, 44.2. Okay, so we want to get from kilowatt hours per day to kilowatts for the size of our system. So we would divide that by hours per day, right? But we don't divide it by 24 hours per day. We divide it by the insulation, which is given to you in hours per day. So the insulation that we just got from PV Watts is 4.44 hours per day. Well, the hours per day cancel out, and we get, looks like it's going to be in the neighborhood of 10. Somebody give me a number.
9.954.
9.95. All right, so that is the size of the array we would need if it were 100% efficient. But we know this system's not going to be 100% efficient. No system ever is. Well, we chose, based on past experience and random guesses, At this point, we're going to derate this at 90%, 10% inefficient. So I'm going to say, all right, 90% derate. So what's 9.95 divided by 0.9?
11.06.
11.06, or basically an 11 kW. If I get a smaller number, it means that I've multiplied it times the D rate. And logically, that doesn't make any sense. If something's inefficient, you shouldn't have to use a smaller array, as compensation for the inefficiency. You'll need a bigger array. So at this stage, then we just calculated that you need an 11 kW system. All right, so that is step number one. So now, what do we do? Well, we can start looking at equipment. So let's say that we need, we're going to do this as a simple string inverter kind of exercise. And it's not how I would design your system. Here, like I said, I would do a microinverter system. So in this case, you need 11 kW. I would go out there and pick a panel. For example, if it were a 350 watt panel, what's 11,000 divided by 350? Still relying on my calculators.
31.42.
31.42. All right, so we could go with 31 panels, 32 panels. We're kind of just in a bit of, it's not an exact science here. So let's say we go with 32 panels and we're going to do microinverters. So now we've got 32 panels, 32 microinverters. We've designed our system. Would this system work if we decided to go with Enphase IQ8s? Well, I know from experience that an Enphase IQ8, I can hook up 13 of these inverters in a branch circuit. So, and to go into a combiner box, I can go in with 4 branch circuits. So if I say I've got 32 panels, I divide 32 by 13, and it's going to be less than 4, right? 3 point something. Because so I could hook up this system in 4 branch circuits and just come down from the microinverters, connect into that combiner box, and then from the combiner box I could go to the AC disconnect, and from the AC disconnect I would go either to the service panel, or I would do a supply side or a line side connection. What is the prevailing issue that we have? Whether we could do a line side connection. Line side connection is going into the circuit breaker box, the service panel, and just connecting at a double pole breaker. So what is our limitation there? Anybody remember?
If there's space?
Yeah, if there is space, that's an issue. If there's no space, well, then you've got some options. You can either get an electrician in and upgrade your panel, or move some circuits around to open up a spot. But that's expensive.
Could you also, I just read in chapter 7 that you could do a sub panel. Is that an option?
Yep, you can do a sub panel, although typically a sub panel has to connect into the main panel somewhere. So it's,
so I have, sorry. So I have, I've got 1 slot left.
Uh-huh.
So would that be enough to go from there over?
Probably. Yeah.
Okay.
The 1 slot, well, what I would need to know about your service panel is do you have 200 amp service coming in from the utility?
200 amp.
Yeah. So assuming that your panel itself is rated for 200 amps, the 120% rule tells us I could come in with a 40 amp breaker into your service panel, right? Everybody remember that, the 120% rule?
Right, but I
So,
don't have room for a double pole, I don't think.
oh, well, yeah, you got problems anyway, because,
Okay.
you know, you're going to be coming in with too many amps anyway. You know, because we just said you've got 32 panels, and each of those IQ8s generate in the neighborhood of like 1.1 amps.
Hmm.
So you're going to be up in the 40 amp kind of range there.
Hmm.
Now, when you multiply that 1.25, you're going to exceed the 40 amp breaker capacity.
Hmm.
So you're going to probably have to go ahead and connect in as a line side connection,
Oh, I see.
which is not that big of a deal.
Okay.
It just requires you're going to have to pay an electrician to come in and do it. But let me just show you what's going to be increasingly a way that people do this more and more is normally on the side of your house. Let's say we've got your electric meter is sitting here,
Yeah.
and then it goes through the wall somewhere. And I'm assuming behind do you have a basement there?
Yes.
Yep. And is your service panel, your circuit breaker panel on the wall somewhere near this meter?
It's like directly behind it.
Oh, it's on the wall right here. So the thing is on, or does it go down below to the basement?
Oh, sorry. No, yes. It goes down in the basement. So it is directly behind it, but down, 6
Right.
feet or 8 feet.
Okay. Yeah. So basically the power line is feeding in here and then connecting into your main breaker behind. So everybody see what I'm trying to demonstrate here. Now, if you were doing a line side connection with your microinverters, somewhere out here near the meter on the wall, you would install the Enphase combiner box. And in here, there are 4 double pole breakers. And you would come in from the various strings from your array, and you connect into these 4 breakers, each of which is rated for 20 amps. So assuming you maxed it all out. Now, from this combiner box, you would then go to an AC disconnect, which has got to be located within 10 feet of the meter. And then from this AC disconnect, you go through the wall and you connect in, hopefully, to a double pole breaker. And that would be it. That'd be the end of it. That'd be your installation with this system. All right. The limitation is if this is 200 amps, then this breaker couldn't be more than 40 amps. So you're probably going to exceed that 40 amp limitation. So anyway, that's problematic, but not the end of the world. So now, if we more and more, what's going to happen is we're going to see. Let's get all of that out of the way a little bit. I'll move the combiner box over. So we've got a combiner box now that's over here. And from here, I'm going to go to my AC disconnect. And then what they're asking for in the 2023 code, which you're probably not subject to just yet, is they want to have what they refer to as a utility disconnect. And that's usually a box that's attached to your meter. And in here, you're going to find your main disconnect. And then there's going to be a double pole breaker here that runs to your main down in your service panel. But because you've now installed this is now the main, and this is really now a sub panel. but they want to be able to turn off your electricity from a disconnect out here. But these boxes can come with multiple double pole breakers. So if
Okay.
you were to install one of these boxes, then you could just simply come from here and hook directly in there, and you wouldn't even have to drill into the building. So this is where we're going in the future, is starting in 2023, really, those areas subject to the code are going to have a box like this outside at the meter. And that will become the logical place to connect into with a solar array at a residential home. You may also want to hook in a generator there. You may want to hook in a battery backup system, things like that. But more likely, and like with the Enphase system now, they have what they refer to as a smart switch. And that's where you would make the connections. You would come from here into your smart switch. You would come in here with your EV charging station. You would come in here with a generator. And from the utility would actually connect in here, and then from here connect into the system. Probably I drew this wrong. I think it would have to come through the meter first. So it would come in from the utility to the meter, from the meter to the smart switch, from the smart switch to that main disconnect. So the reason for this is this this smart switch now can do a lot of things. It's got an auto disconnect. So it's an AC coupled system. So when the grid goes down, this is going to shut down and disconnect you from the grid. So it senses there's no power on the grid, and now you're disconnected from the grid. You're in standalone mode. But everything is still connected together in your home. So you can get power from your solar array. Sun is shining, you're still going to get your solar array operating. You can use your electric vehicle as a battery backup. You can use your generator. You can do load management. You can do all of the different things. You're in standalone mode now. And then when the grid comes back on, it reestablishes the connection here, and you're back in grid tied mode. So this is kind of where we're moving to, where most systems are going to want to begin to utilize their electric vehicle as a battery backup for their home. So that's kind of where we're moving. Yeah, Phil?
In some of those videos that we've seen, all the equipment and everything was outside. I've seldom come across anything outside besides the service meter.
Yeah.
Is it better to have it outside, or is it better to have it inside?
That depends. The reality is most of those videos that you've seen are filmed in Southern California. And so that's fine. You know, I mean, in California, they're mostly outside. But here in Ohio, Illinois, Indiana, you know, it's not a good idea to have them outside in the snow and the wind and the whatever. So typically, I mean, it used to be in the past, people would try and hook them up in the garage. You know, that was a sheltered location, but not necessarily in the middle of everything. To throw a fly in the ointment, the new code is beginning to say all batteries have to be outside. You can no longer put your batteries inside your building if it's an occupied building. They haven't quite defined what that means, because batteries don't operate well when it's below freezing. So, you know, now you want me to stick it outside and it's below freezing. So is it going to properly charge? Is it going to properly discharge? Do I have to put it in a heated cabinet because that's the only way it's going to work? Again, these systems these codes are written by people who live in San Diego, you know, so they just don't even consider this stuff. So that's going to be interesting, but all of these they're evolving. Yeah.
I just got two questions. One, the one thing that I was dealing with, and you pointed this out with my system, is that there's a real estate problem as far as how much room I have. And you had suggested a 350 panel. Would it make sense, because I'm assuming there'd be a real estate issue, to go with, like, I looked online, they have 600 watt panels, they have really high wattage panels. Would that be a solution? Possibly. Obviously, there are other connection problems that you just outlined solutions to. What about a higher panel, assuming there'd be real estate problems?
Yeah, the thing is, the amount of wattage, if the panel has the same level of efficiency, then the real estate that panel takes up, a 600 watt panel will be twice as big as a 300 watt panel, assuming the efficiency is exactly the same. So you would have to get a super high efficiency panel, which is going to be much more expensive. So unless you live in New York City or something where physically you are restrained, you do have space. You can extend that awning a little bit. I mean, I don't think that's going to be economically a good choice for you.
I see.
You could do it. You could do it for sure, but may not be the best. Now, on that awning, you might want to consider maybe a bifacial panel. That will generate some more power for you. Getting some of the reflectivity off the ground under the panel. It's going to be high enough. If you've got like white patio blocks or concrete under it, that's going to reflect up. So usually they figure it costs an extra 10% and generates an extra 15 to 20% power. So economically, it makes sense. You could also get some semi-translucent panels, just for aesthetics. So you're not like in the total shade. It might give an interesting feature to your patio where a bit of light is coming through, almost like a tempered glass kind of situation.
Oh, that's cool.
And you can see the solar cell structure from underneath, which would be kind of cool to let everybody know.
Yeah, that's cool. I like that.
Yep. So there's lots of options. Yep.
My other question didn't actually regard this, but it was something I was thinking about when she said that the batteries had to be. We're moving into a world where the batteries can't be inside a occupied residential home. I was thinking about all the RVers, and certainly RVing has exploded over the last 2-3 years with the pandemic and all, and they've got all these systems where they've got batteries inside their RVs, well, at least in the quote unquote basement compartments, but there's not a whole lot of ventilation and all that kind of stuff. Is there any guidelines they have with those kind of installations in recreational vehicles?
Typically, I think the NEC doesn't really address that, because those aren't considered structures, So I think you're kind of free to do what you do. There may be some other codes associated with RVs specifically. I'm sure there are construction codes and safety codes and things like that. But my guess is who's going to inspect? I mean,
right. Yeah. Right.
Yeah. There's no jurisdiction, so
yeah.
I've dealt with a lot of RVer types who basically they install a small standalone system. They're a 12-volt system for the most part. So
hey, that's one question I did have. I'm sorry if I'm monopolizing. If someone else wants to jump in. And that I'm a little behind. I'm working on chapter 7 now, and I was at the sizing of the battery. Why is it that what's the advantage of RVers using 12 volt rather than a 48 volt? It would seem to me that larger is better, but I defer. I don't know.
Yeah, and you're right. Larger is better. It's just that their system is 12 volt. Their vehicle is 12 volt. Just from historical happenstance. So if they wanted to use their vehicle as a generator, basically, they'd have to operate at 12 volts to, let's say their batteries are going low, but they want to recharge them from their vehicle. They could just start up their vehicle and use it as a generator. But you could install a separate 48 volt system in an RV, no problem. It just would be isolated from the vehicle itself. So normally in those, they install a 12 volt DC system without AC conversion, so if you're getting it from the manufacturer, although more and more, because the efficiency is there, they're getting some AC, jump over to AC as well. So there's lots of options. Marine, it's not just RVs, but boats as well, have that as a idea. So
thank you.
Sure. Any other questions on that? Otherwise, I'll jump back into your design. I mean, from anybody about anything, meaning of life, what's the capital of the Honduras, anything like that. Okay. So let me jump back in here, trying to see what you guys might. I was sort of here in a world of microinverters, which wasn't really how I was thinking about installing this system. But let's say if we do a straight string inverter system, now we're sort of not on your property, but we're just theoretically saying we're going with an 11 kW array. So one of the first things we'd want to do is we'd want to jump in and select a panel. Now, when you were talking about panels, so you're going to find, it used to be, let me see, Philip, are you seeing Alti's website here? Okay, good. I like Alti's website. Not necessarily, I don't want to necessarily buy the stuff from them. I just find it's easy to navigate. But used to be, if I went in here to buy some solar panels, I would find 30 or 40 different options. Well, now this is the options that they have. Alti has just on one page. Used to be 6 or 7 pages you would get. So supply chain constraints have left us in a bit of a quandary. Now it's currently listed by watts. Well, look at these 20, 30, 40, 90 watt panels. Well, that's not going to help me much. Those aren't really residential size panels. These are little tiny things. They're, almost toys. So it's not until we get up into this particular panel here, this Hylene, before we start getting real residential panels. So if I go into Alti, basically Alti's telling me I've got 5 choices of panels if I want to buy from them. I can buy a 360 watt Hylene panel, and that's going to be 79 cents per watt. I could buy a Trina bifacial, $3.95. I could buy this Canadian Solar, $4.55. So now you're getting into panels that probably won't work with your microinverters. This Trina 500 or this Bicram 540. So these are some bigger panels that will not work with those IQ8 microinverters from Enphase. There are microinverters that will take that size panel, but not the IQ8. I think it's limited at like 455, something like that. So if we decide to go with microinverters, you really got 3 panel choices if you're going with Alt-E. So let's just say that for the heck of it, we've decided we're going to go with the Hylene 360. So the thing that I need to know in here is what is the open circuit voltage. So this is showing me, I've actually got a 320 and a 360. So the open circuit voltage on here is 48.62 VOC. The short circuit amperage or current, 9.41 amps. I think that's all I need at the moment, but I'm going to go ahead and put the VMP, 40.45 volts. And the IMP, 8.9 amps. The other thing that I need is what is the temperature coefficient? Now with Alt-E, typically you'll find that in the data sheet. And for this particular one, we'll find it down here under temperature ratings. So at Pmax, which is, or at VOC, it's showing me that it's minus 0.257% per degree Celsius. Okay. I think that's all I need at the moment. Or, well, I will need the Pmax. That's what we're going to be using if we're dealing with VMP. So that's 0.294% per degree Celsius. So that's VOC. I'm making some notes here. All right. So let's go ahead and jump back into our calculations. So at this point, what I'm trying to do is calculate string size. Okay, so I think I've got the data that I need. So hopefully, if you remember, if we're trying to figure out string size, then I want to know how many of these I can put in a string. What is the maximum number? Well, the first thing I need to know, and I'm not going to look it up, but I'm going to make an assumption that the coldest temperature ever at that location. I haven't looked at recently. What were some of the temperatures we were assuming in some of those problems? Is it minus 40 maybe? Does that sound right? All right, we'll just say it. You live in a very cold place. All right, so coldest temperature ever, minus 40 degrees Celsius. We just found that the what is VOC, or what is standard test conditions? 25 degrees Celsius. So the delta between the coldest and standard test conditions is going to be 65 degrees Celsius. Okay, so now we found the difference. Well, what is the temperature coefficient on this panel at VOC? Well, we looked that up and it turns out it is 0.257% per degree Celsius. All right, so what is 65 times 0.257? Waiting on a calculator.
16.7.
16.7. Now the degrees Celsius cancel out, right? So now it's just 16.7%. What does that mean? It means that on the coldest day ever, this panel will produce 16.7% more volts than it would under standard test conditions. So we add that to 100%. Well, what is the maximum voltage that panel might produce under standard test conditions? Well, we looked up on that spec and it said VOC was 48.62 volts times 1.167. That's 116.7%. So what's 48.62 times 1.167? Anybody?
$56.73.
56.73. So on the coldest day ever, that panel might produce 56.73 volts. Assuming we've picked a string inverter that operates at 600 volts, 600 volts being the largest that we can do for a residential system. So 600 volts divided by 56.73 volts is it 10 point something?
10.5.
10.5
Yep.
panels. And you can't have part of a panel, so we round down. So 10 panels max. Now, I'm not going to figure out the minimum, but what we would do with the minimum is we would say, all right, we take the hottest temperature ever, find the delta between that and 25. Then we add in, this is a roof mounted system, so it would be, we'd add 35 degrees Celsius. If it were ground mounted, we'd add 25. If it were ballasted, we'd add 30. And then we use the temperature coefficient at VMP, and then it's going to be 1% less. And then that will give us our minimum, and then we'll have to look at the startup voltage of the inverter. But it's pretty much the same process. Well, we said this was an 11 kW system with 32 panels. So how many panels in a string? 10 panels max. So I could do 3 strings of 10, or I could do 4 strings of 8, right? 4 strings of 8 is going to get me right in there at 32. So I'm going to say this is 4 strings of 8. So that will give us our strings. So let's say we come out of here with 4 strings. What's going to be the amperage of each of these strings? Well, we looked up the ISC, and the ISC on this was 9.41. 9.41 amps. So we multiply that times 1.25, which is the NEC. And then we're going to multiply it times 1.25 again, which is the solar variability. And that's going to give us
14.7.
What is that, Philip?
14.7.
14.7, is that right? Everybody agree? All right, so what size wire would we need? Well, we'd have to look on page 104, but I can tell you it's going to be 12 gauge. That's what comes in with the panels. That'll go up to 20 amps. All right, so let's say we come into a combiner box in this case, because I want to come in with 4 strings, but I want to leave with only 1 string. Okay, this is sort of the old-fashioned way of designing. So we know that each of these is coming in at 14.7 amps. So if I put a breaker in here, I would round up to the next commercially available breaker, which would be a 15 amp breaker. So I would have 15 amp breakers in my combiner box. What would be the ampacity rating of the wire coming out of that combiner box?
58.8, that is 14.7 times 4.
That's right, exactly, because we're combining 4. We've already derated it with these factors. So you say that's 58.8 amps. Okay, so I'd look up on the wire gauge on page 104. And remember, the trick that you want to do is even though different wire temperature ratings will allow you to select different size wire for different, the higher the temperature rating of the wire, the more ampacity it'll carry. But the wire circuit is not just the wire, it's the connection points at both ends of the wire. And those also have temperature ratings. So the connection point in the combiner box, and this is going to go to a DC disconnect. So the DC disconnect is also going to have temperature rating at that point of connection. At this point, we don't know what those are. We haven't selected that equipment. So we have to assume the lowest rated temperature wire. So you always get your ratings from column 1. Okay, so if anybody's got the book, turn to page 104. I'm pretty sure it's 104. And if you look in that table, you're going to find that in column 1, 6 gauge is only rated to 55 amps. So we can't use 6 gauge. We're going to have to use 4 gauge. So this wire right here is going to be number 4 AWG, and it is rated to 70 amps. Okay, now I'm going to come into a DC disconnect. Well, the DC disconnect itself is also rated for amperage. Usually these disconnects come in 30 amp, 60 amp, 100 amp ratings. So in this case, I'm going to go ahead and get a 60 amp disconnect because I'm coming in with 58.8. If there is a fuse in your disconnect, which I would recommend, well, in this case, it's going to have a 60 amp fuse as well because you're coming in at 58.8. Don't worry about the 70 amps. That's just the rating of the wire. From your DC disconnect, we come in and we're going to go into our string inverter. What size wire will be from the DC disconnect to the string inverter? Well, nothing's changed, right? Still going to be 4 gauge, still going to be 58.8 amps. It's just that you put a disconnect in the middle of it. So that continues on. So now we're coming into our inverter. Well, what size inverter do we need? At this point, I'm going to go in and I'm going to go back to Alt-E. I'm going to, whoops, nope, I went to the wrong screen. Trying to see. It's hard for me to tell in my little. Oh, here it is. Yeah. Okay. So now I need to go in and I need to buy an inverter. So in the Alt-E inverter, I want a grid tied inverter. And I've got some choices. I can go with a Fronius. I've got a 10 kW Fronius. I've got an 11 kW. I've got all these other options. I've got some Fronius Primos down here. Different choices. Now we get down here into the Solar Edge. So let's just say I'm going to go with a Fronius 10 kW. Well, remember our array is 11 kW. So can I use a 10 kW inverter on 11 kW array? Yeah.
Yes.
Yes, for sure. That gets into what's known as clipping. And in this case, pretty easy to figure out. The inverter load ratio is going to be 1.1, right? 11 over 10. So I've got a 1.1 kW inverter. Now, as I'm looking here, it's telling me all Fronius Primo inverters are on extreme back order. So supply chain issues. But because we know the people at Alt-E, they put us to the front of the list. So we're going to go ahead and buy this thing anyway. All right. The reason I want to look in here is I just want to see what is the, here's where your specs are. It's telling me my maximum input is going to be, well, it's well within, because I know it is. Recommended breaker 70 amps. It's got a 96.7% efficiency. So we'd use that number when we're derating our system. We just assume 10% at this point. It's telling me the conductors. Normally, I might have to look at the specs. Normally, it should tell me what the output. Oh, here's the input. Here's the output. All right. Maximum input, maximum output. Oh, that's in watts. Maximum output current. Yeah. Okay. So 208, it's got an output current of 48.1. 240 single phase, it's got an output current of 41.6. And that's kind of what I wanted to see. So this inverter will output 41.6 amps right there at the point of output. So let me go here, go back into our whiteboard. So I know that from here, it's telling me it's 41.6 amps. Well, because we no longer have solar variability, I just multiply this times 1.25 because that's the wire safety. So what's 41.6 times 1.25?
52.
52 amps. All right. What size wire do I need? Well, if I look at that same table, 6 gauge will take me up to 55 amps. So I need 6 gauge. From here, I'm going to an AC disconnect. From the AC disconnect, what size AC disconnect? Well, 30, 60. So I'd put a 60 amp AC disconnect. If I put a breaker or a fuse in there, I'd put a 55 amp fuse. And from here, you might want to do a load side connection. Well, if I've got 200 amp panel with 200 amp service, I can only come in with 40 amps. And I'm actually coming in with 52 amps. So this would not work in this situation. Now, there are some ways we could make it work. I could have the electrician swap out that 200 amp breaker from the grid to, let's say, a 180 amp breaker, and now I've got enough capacity. Or alternatively, I might go to a supply side connection to where I tap in somewhere between the meter and the main disconnect. Okay, and that will allow me to make this connection. So that would be a supply side connection versus a load side connection. Okay, so we've just designed your system using a string inverter, or we could have just gone 32 panels, 32 microinverters, boom, 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 we're done. So.
Thank you.
All right, well, that took up pretty much the whole hour. This is the last session of this as far as our review session. If you have questions, keep getting in touch with me throughout the week. I'll be happy to continue to answer those questions as you work your way through the system. This coming weekend, we're doing the class in Oberlin. So Oberlin, I'll send you the room and the building specifics on this. Shannon told me that he thinks, so I don't have this confirmed, that it's in the AJLC building, either room 102 or 202, but I'll get the specifics on that. We'll be meeting Saturday morning, 8 o'clock. So that will be it. For the folks in Indiana and the people at Hiram, I'll get those specifics before we have, you guys have a little more time to prepare. But the folks in Oberlin, it's coming up this weekend. So if you haven't gotten through the whole session online, you've got a couple days left. It's like tax season. You can be doing it till midnight the night before. So, all right. Any questions? Last minute questions before we say adieu? All right. Then I'll talk with you all later. Take care. Bye-bye.
Bye.